so this is the FP2 paper from 2019, Pearson Edexcel A-level further maths. Let's go into it then. So z equals x plus iy, so replace those with x plus iy's. Our aim here is to group up the real parts and the imaginary parts separately. So this will be x minus 3 and then plus iy, and this will be x plus 1 then plus iy. And the reason you want to do that is because if you have a complex number like this in a modulus, then that's of course just the root of a squared plus b squared. No I is necessary. So here, this is just the a and this is just the b. And we can get rid of the i's by doing this root here. But first we should probably just square both sides, because then we just end up with a nice a squared plus b squared. So if we square both sides here, we'll get, of course, 4 squared has to be done separately. But here we'll just get x minus 3 squared plus y squared. And that will be that, just based on this. And likewise for here. And yeah, the 4 just expands out to be 16s, right? And from here, we just need to expand everything out, collect everything together, and eventually it just ends up being a nice little circle looking a bit like this. I did this in the calculator mostly, obviously, and we end up with a circle of this form, I think. So good, that's the, I think, actually, no, okay, so I finished the first part here, right, I guess, and then I continued a bit and found the center and the radius of the circle there, square rooting that to get the radius being this. Now find the maximum value of the modulus of z. We'll just draw a picture, right? This has center minus 19 over 15, 0, which is over there somewhere, and radius a little bit less than where the center is. So the circle doesn't quite reach the origin. That's kind of irrelevant though, because of course where the modulus is going to be biggest is when you're furthest away from the origin. And the furthest away from the origin on this circle is of course here. So all we have to do is do this 19 over 15 plus the radius 16 over 15, and we'll get our answer for the furthest distance away from the origin, which is our maximum value of z modulus, or whatever. Good, okay, so that's question 1. Question 2 is about eigenvectors and eigenvalues. I'll say my usual thing here, which is that if you haven't watched 3 Blue 1 Brown videos, his video on eigenvalues and eigenvectors, I don't know what you're doing with your life, because you should just go watch it. But of course we'll just take lambda away from all these diagonals here, and then do the determinant of the matrix, and we'll set that to be 0, and we'll see what happens. So it's going to be this into this times this minus this times this, minus this into this times this minus this times this, and then plus this into this times this minus this times this. That's going to be the system, isn't it? It ends up being all this. You can just check that I've put that all in right. You should know how to work out the determinant of a 3 by 3. It's in core pure, isn't it? You expand everything out exceedingly carefully, just like exceedingly carefully. Just don't make a mistake here. I've times it by minus 1, just give me a positive here. Show that 2 is a repeated eigenvalue. Well, I can show that it's an eigenvalue just by substituting 2 into this and verifying that it does actually work, which it does. So 2 is an eigenvalue. How do I show it's repeated? Well, what I could do is I could take this cubic here and I could divide it by lambda minus 2, because lambda minus 2 must be a factor through factor theorem, regular A-level maths. However, I'm not going to do that because I hate polynomial division. So what I'm going to do instead, I'm just going to say, well, this cubic here is going to be factorized lambda minus 2, because of that solution there, into some other quadratic. And I can just spot the coefficients, like lambda times lambda squared makes lambda cubed, means there's just a 1 here. Minus 2 times plus 16 makes negative 32, so that's a plus 16. If you just call this a for a second and look at the lambdas, you've got 36 lambdas over here, and you've got minus 2a over here, and also plus 16. So minus 2a plus 16 is equal to 32, or sorry, equal to 36. And of course we can just solve that to get a as minus 10, and that will be our fully factorized. Sorry, that will be our factorized form. Our fully factorized form, that factorizes to lambda minus 2, lambda minus 8, I believe, which is great because now we've shown 2 is a repeated eigenvalue, and we've got a third eigenvalue of 8 here. So good. Cool. Hence, find 3 non-parallel eigenvectors. So let's run with the eigenvalue of 2 first. I think we're going to get two eigenvectors from 2, and then we'll get 1 from the 8. So let's substitute in 2 into here, put lambda as 2 into AV equals lambda V. That's of course the formula for eigenvalues and eigenvectors. So we put that into here, and we read them from the top row. This into x plus this into y plus this into z equals 2x. That gets me this. This into x plus this into y plus this into z gets me 2y. And likewise for the last row. We can take away 2x, 2y, and 2z from all of these to get these. And now here you're never going to have, you did this in core pure somewhere, either book 1 or 2. This is never going to have a unique solution when you're doing eigenvectors. And you know that because, of course, these vectors could just be multiples, right? Like if the vector 1, 1 was a solution, if the vector 1, 1, 1, I guess, was a solution, then so is the vector 3, 3, 3, right? Because lambda would just, so you're always going to have multiple solutions here. So what you want to do is you just want to pick a value that might work. The other thing you might notice from here, of course, is that actually this is just a multiple of this. You just times by -2 and you get this. So that doesn't mean anything, it's useless. But also, actually, if you just times this by -1, you get this. So actually, this is basically the only thing you have here. The other two are completely pointless because you're just timesing by -1 or timesing by 2. So we'll just ignore those and we'll just deal with this. And of course, this has an infinite number of solutions. So just set x to be 1 and y to be 1, maybe, I guess. And that forces z to be, or 2 minus 1 is 1. So that forces z to be -1. And that's one eigenvector that you could use. Or you could set, say, y equals 1 and z equals 1. And then that will actually cancel here and you get 2x is 0. So x is 0 and you'll get another eigenvector. So just when you're getting to this far, there'll never be a set solution, so you don't need to do any proper maths to try and find it. Just set some things, just come up with an x and a y, and you'll find a z from there. Anyway, those are for those two, and then we'll use 8 to find the third eigenvector. So put in 8 into here. Do exactly the same thing. You actually end up with 3 different equations here. That doesn't mean you're going to have a unique solution, of course. Just let x equal 1, for instance, and you'll get maybe these two equations here. I think I've just set x to be 1 into these two. And then I actually went ahead and solved these. So I think I times this one by 5 maybe, and then did this minus this. That looks, times that by 5 to make -10, and then 2 minus -10 is 12. So z is a half, and then you also get y as a half, I believe, or minus half if you go back into there. And so this will be an acceptable eigenvector. Good. Of course, there will be other things you could have got if you didn't choose x to be 2. For C, then, find a matrix P such that this happens. You just take these 3 vectors and you put them into a matrix like this. And yeah, that's simple as that. Good. Question number 3. So we've got something about recurrence relations here. So the number of visits in a month is modeled by the number of previous visits plus k times the number of visits before that. So it's going to be Vn plus 2 is equal to Vn plus 1 plus k lots of Vn. Therefore, visits this month is equal to the visits in the previous month plus k times the visits in the month before that. Good. So k is 0.24 apparently, and we've got v1 is 65, we've got v2 is 71. It just wants us to solve this recurrence relation here. So we get the auxiliary equation out, which is r squared, and if you rearrange this, you get this minus this equals 0. So we're getting r squared minus this, it's just r, minus 0.24, lots of this blank thing here. And then, of course, you can spot the factorization mostly because you're given it, right? 1.2 and minus 0.2 is what we're looking for. And it does work, so that's good. So solutions are at 1.2 and minus 0.2, which you have been told, which is helpful. That means the answer is Vn equals a lots of this thing to the power n plus b lots of this thing to the power n. This is just the standard setup. If you've got 2 distinct real solutions, it's different if you've got complex or a repeated one. But we've got 2 different real ones, that's fine. And now we just need to use these values here to find a and b. So set of n equal to 1, and you get v1 is 65, and the 1 is just 1.2, the 1 is just this. And set n equal to be 2, and you get 71 equals these things to the 2. I won't bore you with the solution to this simultaneous equation. Eventually you end up with this. You can actually just even type it into a calculator, I guess. And yeah, we show exactly what we were required to show. The model predicts the number of visits will exceed 1 million for the first time in month n. Find the value of n. So we're going to be doing this here. The dumbest possible solution to this is to just try values of n, which is, of course, exactly what I did. If you plug in 20, you get this number. I then went for 50, I got this number, which is about halfway. I then went to 55, I got this number, which is just over. And then 54 is just under, so therefore 55 is the answer. If you want to do it in an actually intelligent way, what you say is, when n becomes really big, 0.2 to a really big number is basically nothing. So you just ignore this term entirely, because it's just going to be meaningless after like the first few n's. Then you, of course, so you just say, okay, well, when is this just equal to this? You divide by 50, you take log of 1.2 to both sides. That equals that. And so, of course, n needs to be bigger than this, so n needs to be 55 or bigger to be the correct answer, which is what we also got there. Use Fermat's little theorem. So what is Fermat's little theorem? It says any number to the power n minus 1 is congruent to 1 mod n, where n is a prime number, so it's usually written as p. So if you've got 13, which is prime, any number, in this case 6, because that's the number there, So the power of 12 is congruent to 1 mod 13. This just has to be 1 less than that. So okay, how is this helpful? Well, 542 is equal to that many 12s plus 2. So what I can do is I can write 6 to the 542 as 6 to the 12 times 6 to the 12 times 6 to the 12, because of course all of these just add together, don't they? So if I put 45 of them together, that's going to make 540, and then another 2 would give me the 542. But congruent mod 13, all of these just go away. Like if you just take mod 13 of this, that's a 1, that's a 1, that's a 1, that's a 1, which from here. So this is just 1 times 1 times 1 times 1 times this. So that's just congruent to 6 squared mod 13. 6 squared is 36. 13 times 2 is 26. This is 10 mod 13, and we'll have answer of 10. Good. 7 students are in a constant. Find the ways they can be seated with no restrictions. So you've got 7 choices for the leftmost seat, 6 choices for the next, 5 choices for the next, then 4, then 3. It's just 7 factorial, which is this number. If these people sit together, what you can do is you can kind of group them up into one super person, and then you can say, okay, there's this group of 1 person, and then there's 3 other people that aren't part of the group. So now you've just got 4 people to sit, and that's just 4 factorial. Except then, once you've sat those people, so maybe you put these 4 first, then one of the others, then one of the others, then one of the others, you can then rearrange these 4 in their little mini row. And there's also 4 factorial ways of doing that. 4 times 3 times 2 times 1. So it's just this times this, and you get that. Brenda sits at one end, Graham sits at the other, so put Brenda on the left, put Graham on the right. There are 5 more people to sort, so that's just 5 factorial. But Brenda could have been on the right, and Graham could have been on the left, so we just have to times it by 2 after you've done that, and you'll get your answer. These 2 do not sit together, similar to this one, except this one was sitting together. So just take the total number of ways you can do it, minus the number of cases where these 2 do sit together. So it's going to be the total number minus, and then similar to here, group those up to be 1 person. You've got 6 people now, because these people are pretending to be 1. That's going to be 6 factorial, but then you times by 2 because you could swap these 2 over. So it's going to be 6 factorial times 2 factorial, I guess, which is just 2, and then it's going to be this minus that, and you'll get your answer there. Question number 5, really nice. I love these questions. I just think they're the best questions in the paper. So what do we do here? Well, we'll deal with the first bit. First, we need to show this thing. It's always an integral by parts first. So we look at this and we go, okay, how do you integrate that by parts? Well, one option would be to times it by 1 and try and do it that way. But I notice that there's an n minus 2 over here. So I'm going to go for the other option that you see a lot, which is breaking this up itself. So I'm going to break it up into cosec squared and then cosec n minus 2. So that's how I'm going to break it up. And now I'm going to aim to do integral by parts on these 2 bits. Now this is the thing that I'm going to integrate. And I look in the formula booklet and I see this here. Now this is not in the integration section, but it's worth noting that this is just as useful sometimes as the integration section, because what this tells us is that this thing differentiates to this thing, which means of course that this thing integrates to that thing. So I think cosec squared I can just integrate to minus cot. So that's cool. So when I do my integral by parts, I can integrate this one to minus cot. I can leave this one alone. I can take away the integral of, again, integrate that to minus cot, and then differentiate this one. That's how I do it in my head, is integrate, leave alone, differentiate, minus integral in the middle. Okay, so differentiating this to where you bring the n minus 2 down, obviously. You take that and it becomes an n minus 3. And then you times by the derivative of cosec x, which is also very helpfully in here, this table here. It's minus cosec cot. So that goes there. Good, so let's tidy this up a bit. So obviously cot and cot make cot squared. There's a cosec here which will bounce that back up to an n minus 2, which is very helpful. So that I think we get this, a bunch of minuses go away, and then this you can bring out to here. So we've got this now, and how do we deal with this? Well, let's deal with the cots. There's a identity using cot squared that's quite helpful, based on this original one. If you divide everything by sine squared, you get this. Cos over sine is obviously cot, so cos squared over sine squared is cot squared. And I think that's quite helpful, because I can rearrange to make this, and I can put that into here. And that's the hardest thing about this question, I think, is figuring out how to do that. And then, of course, we can just expand this out, and we'll get this. And then, of course, we can do this integral separately. I can integrate this, and then integrate that separately. But what's nice about that is that, of course, that this is in, based on the definition, and this is in minus 2. And I think we're pretty much there now, right? We're going to get this now. Because all we have to do is bring the in's onto one side, so like this, and then factorize out from this one, so it's one lot of it falls from here, and then the n minus 2 is over from over here. And then, of course, I've just moved this to the end as well because it's got a minus there. And then, of course, this is just n minus 1. You can divide by n minus 1, and you'll get... I've written this completely wrong. That n minus 1 shouldn't exist anymore. This line is correct, and then you divide both sides by this, and you get this, and this should have gone away. So I just copied and pasted and didn't go to it, so apologies for that. Good, so that's the harder bit of the question, is getting that. Now we get an extra 4 marks for actually doing it. So okay, well, n is 6, clearly. Right, so we're looking at I6. So this is I6 between these two bounds. I think I just completely ignored the bounds until the very end, to be honest. I6, of course, is just this, where you put 6 in to these places. So that's what I've done. But now, of course, that simplifies to this, obviously. But I4, of course, you just do it again. I4 is just this with 4s in there. So let's do that. Let's just put some 4s in there and then tidy it up. And I2, now you can't use this formula for I2. I mean, apparently you can, actually. But if you did, I don't think it would be amazingly... Would it be helpful? I don't know. Maybe it would have been helpful. Maybe you could have done it again. What I actually did was, obviously, I took it from here, and I actually just integrated cosec squared because I thought I could do it. In fact, I'm very confident I could do it because we've already done it. We already know that it makes cot. So I can replace that with a... technically, it makes minus cot, doesn't it? So I should have had a minus in here. Where's that minus gone? Interesting. There should probably be a minus in front here. Unless I'm not mistaken. I think that's just a mistake on my part. I haven't actually bothered. So what happened then was I was happy with this integral, and then I just put the limits in, but I don't think I actually ever bothered doing them. Oh no, I actually totally did. So I don't know why this minus cot has just managed to not be a problem. There should be a minus in there somewhere, and then this math should turn out to be exactly what they wanted it to be, which it did for me. So I don't know how I managed to get the right answer here, having missed a minus up here. So that's a bit of a problem. Maybe you can pause the video here and find my mistake, but my logic is all correct. It's also possible, I guess, going back. I think it would have totally been possible to just use this formula with I2, or with n is 2, and reduce it further, and then you get down to I0, which is just the integral of 1 dx, which would have been maybe easier than actually doing the integral. But in any case, this is roughly what it should look like, and that's roughly how you do it. And I'm just going to accept that that's fine. Good. Question number 6 is about groups. So firstly, proving associativity. This is associativity that when you do the operation twice on 3 different things, it doesn't matter which order you do it in. That's essentially what that means. So okay, well, let's just do it then. So let's start with the left-hand side. A star B is this, so let's put that there. And then start with C, which means just look at this and replace the A's with these and put them over here. So I think it makes this. You have this object first, then you have this object, the second one, then you have this object times this object. So that's that. That expands out to make that. The right-hand side then, let's look at that. So B star C is just this with B's and C's instead. And then same thing again, this object, then this object, then this object times this one. When you do that though, you just get exactly the same thing. And so therefore this is associative, which is good. 2 then, we have this set G, which is modulo 7 multiplication. Show G is cyclic. Now to be cyclic, you just need to find one thing in G and show that if you just apply it, the operation to itself a bunch of times, you can create all of the others. Now 1 clearly doesn't work because 1 times 1 is still 1, times 1 is still 1, times 1 is still 1. You're not going to get any others. 2 also kind of clearly isn't going to work because it's even. So 2 times 2 is 4, which is this one. 2 times 2 is 8, which is going to give you another even one. No, in fact, no, sorry. 2 is it's going to go to 1, isn't it? Because it's mod 7. Anyway, 3 is the one that works. 3 to the 1 is 3 mod 7. 3 to the 2 is 9, which is 2 mod 7. 3 to the 3 is 6, which is, is 27, which is 6 mod 7. And this all just works. It's just a case of finding the one that works. 5 also works, which is going to be helpful to know later. But this isn't enough to show it's cyclic because you just need to show that it works for one of them. And we also call 3 a generator, I guess, if it does that. Next we have another set H. So I've done this first bit. We have H that is similar. It's got 6 things here and it's modulo 18 this time. Lists the subgroups. Now a group has to obey these conditions here, these 4 conditions. Now I don't think I need to care too much about associativity because we kind of just know multiplication is associative, so I don't think I need to show that very much. But I do care about making subgroups that do these things. So any subgroup I make has to be closed within that subgroup. It has to have the identity, so all the subgroups must have 1. And each element must have an inverse, which means there must, if you take 5, you must also in that subgroup have the other one that multiplies by 5 to make 1. So okay, what I tend to do here is just write out the multiples of 18, because that way, when I'm looking at 5, for instance, I want to find 5's inverse. So which one of these is just 1 below a multiple of 5? Well, that is 5 times 11 is 55. So great, okay, 5 times 11, those are the inverses. 5 times 11 is 1 mod 17, because it's 1, sorry, mod 18, because it's 1 above that. So 5 and 11 are inverses. And that's useful to know, because when I'm making subgroups, it means I have to take, if I'm going to take 5, I have to take 11, and vice versa, because they make each other's inverses. Likewise, you can search some more, but for 7, multiple of 7 here, that's 1 more than these things. I can't even see it right now. 90, there it is, 91. 7 times 13 is 91. So 7 and 13 are a pair. And 17, now 17 is minus 1 mod 18. So it's kind of obvious that if you just do 17 times 17, minus 1 times minus 1 is 1, and so 17 is its own inverse. So that's quite good to know. The last thing that I need for the subgroups is Lagrange's theorem, which says that the number of things, or the order that you have in the subgroup, so the number of things in the subgroup, has to be divisible by the order of this. Now the order of this is 6, there's 6 things here, so the only possible orders of any subgroups are things that are divisible by 6, or things that are factors of 6, I should say, actually. So 1, 2, 3, and 6. These are the only number of things I can have in my subgroups. So of course, if your subgroup only has one thing in it, that's just the subgroup 1. And if your subgroup has 6 things in it, that's just the whole thing. So that's 2 groups of 3. Now, what about groups that are too big? Well, you must take 1, because you've got to have the identity. And the only other thing you could take, you can't take this, because then you need 11. You can't take this, because then you need 13 for the inverses. But you can take 17, because 17 is its own inverse. So I think that works as a subgroup. This one here, so where you take 1 and then you take these 2. This one here, where you take 1 and these 2. So now we're looking at order 3. There's no other way to make an order 2 one. And order 6 is obviously just all these. Now one of these doesn't actually work, which is this one. And the reason it doesn't work is because if you took like 5 and then multiplied by itself, 5 times 5 is 25, which is 7 mod 18. So this actually doesn't work because it's not closed. The subgroup isn't closed. I can generate other things that I didn't get, that I didn't take into this group by using 5. So that actually doesn't work. But this does, because 17 just generates 1 and minus 1 over and over again, because 17 is minus 1 mod 18. And this one does work as well, because again, these two just kind of swap between each other, which is good. But you can test that yourself to make sure that they do that. This one, of course, works because it's all of them. Good, so now the hardest bit of this question, I think, describe an isomorphism between G and H. So what it wants you to do, now how I tend to do these questions is just gather as much information as I can about the two groups. So we already talked about how 3 is a generator of this group and so is 5. We also, maybe what I want to do is write out the multiples of 7 and find the inverses of these things. So 2 times 4 is 8, which is 1 mod 7, so 2 and 4 are each other's inverses. And also then 3 and 5 are, because 6 inverses with itself, just like 17 did, because it's minus 1 mod 7. And of course 1 is an inverse as well. So these are the 3 sort of pairs that go together to make their own inverses. And I've done the same thing for H, right? We've already talked about these pairs that work here. And now the generators for H, we also sort of talked about the fact that 5 could generate 7. And by multiplying itself, you can test it a bit more, but 5 and 11 are both generators of this group here. And now, when I'm doing an isomorphism, what I want to do, I can't really even say that word today apparently. What I want to do is I want to essentially write out the elements of H underneath here, such that each element, essentially in this group, behaves exactly the same way as the element above it behaves in this group. Now, 1 must just behave the same as 1 does, right? That's kind of obvious, because it's just 1. And likewise, 6 just behaves the same way 17 does, because they're both the minus 1 mod their respective thing, and just go from minus 1 to 1 to minus 1 to 1 by themselves. Now the less obvious ones are these ones here, but that's why I've got all this information, right? So in an isomorphism like this, these two pairs, like if there's a generator here, there must be a generator here. So the only thing that can go below 3 here is 5 or 11, and likewise the only thing that can go with 5 is again 5 or 11. So the generators must match up, and the non-generators must match up. But also these pairs must match up with each other as well. If you want to go full overload with this, you can draw a Cayley table for G and H. This is how the book recommends to do it. Jay Winfield actually helped me to put this Cayley table in Excel. He knows how to generate them automatically, which is super fun to know. So, call him up if you need him to do that. But these are the Cayley tables for G and H. So like 3 times 2 is 6 mod 7, whereas 5 times 4 is 20, which is also 6 mod 7. So that's how this Cayley table is working. And what we can do is we can say, okay, we'll just look at 2 times 3. Right? So 2 times 3 is 6 mod 7. Now 6 we know is the same as 17 over here. So what 2 things can multiply to make 17? Well, one thing is 5 and 7. So what I've sort of said there is that 2 and 3 could be the same as 5 and 7, because 2 and 3 make this element, and so do 5 and 7. So that's how this isomorphism could work. Of course, you could swap those over and get 7 and 5. Or, of course, looking at this, you can also use 11 and 13. That would also work, and likewise the other way around. But what I've already said is that the generators must match up to each other. So 3 can't match up with 7 because 7 is not a generator. So 3 can only match up with 5 or 11. So actually those 2 options are gone. And likewise, you could do the same thing over here. Like 4 times 5, looking at the Cayley table, 4 times 5 is 6, because of course it's 20. Mod 7 is 6. 6 is isomorphic to 17. So these two here must multiply to make 17. But again, that's the same list we just came up with, right? Multiplying to make 17. But like I just said, 5 needs to match up with a generator, so that can only match to 5 and 11. And these are the only options we have. We could pick 7 and 5 to go here, and we can't pick 7 and 5 again because we need all of the different elements here. So we could put 7 and 5 here, and then 13 and 11 here. Or we could put 13 and 11 there, and we could put 7 and 5 there. Those are the only 2 options that you could have, and either one would do. Good, so I probably way over explained that, but you've got plenty of time in the exam, so maybe thinking it through that deep would be helpful. I don't know. I don't really know what question 7 is doing on this paper because it's really easy, and we've also done complex numbers in this paper before. But anyway, we'll take it. It's 3 marks, so we'll take it. We just need to rearrange this for Z. I won't bother talking about that in great detail. We plug this into here. We work out what this is together. So I'm just doing this. I'm just doing some very basic stuff here. You end up with this. When you do the mod of a fraction, you can just do the mod of the 2 things separately. The absolute value of -1 is obviously just 1. We can multiply this across to here, and we end up with this. Of course, the mod of 3i minus w is the same as the mod of w minus 3i, because whichever one of these is negative, the mod just makes positive anyway, so we can just do that. This is a circle, because it's some complex number, minus 3i size is 1, so we're 1 away from the point 3i, which is a circle radius 1. But of course it also wants the Cartesian equation, so we'll just substitute in x plus iy for w. We'll do the same thing reading question 1, we'll group the i's together, we'll square out this one and this one to get rid of the I and the moduluses, and we'll end up with the equation of a circle here, which we can draw, right? This is center 0, 3, which is up there, radius 1. Maybe I should have put a 3 here, but whatever. And this circle here, circle C, is just center -1 down here, isn't it, on the imaginary axis, radius 1. So our pictures look like this. Good. The last question I thought was quite a tough one, just to understand what this curve is trying to do. So this curve is this, apparently. Now, let's just think this through before we start. When theta is 0, cos of 0 is 1, so you get r squared is 25, so r is 5. So wherever the initial line is and wherever you're starting, r is 5 when theta is 0. And initially that doesn't seem to make much sense here, because like where are you going to put the initial line? Like theta is 0 means you're traveling across, right? And radius 5 means you go across 5 from the initial position. So where would that match up to here? Well, there's a 5 here, which seems too coincidental, but it's going downwards. So eventually what you realize is the initial line in this is actually a downwards line, and you're starting here. And when theta is 0 is along this line. When theta is 0, the radius is 5, and you start here. And then as you increase theta, you sort of move your way along this curve here until you get to here. And now, what is this point? Well, cos is going to become negative eventually, isn't it? Which will make this whole thing negative, and then you can't root it. So when theta is pi over 4, cos of 2 theta is cos of pi over 2, which is 0, and then r is 0. So I think this line here, coming out here, I think that's pi over 4, because then you get round here, and when you get to pi over 4, you end up there. And when you go over pi over 4, this is negative, and you just don't draw anything. And then you come back out here, I think, when cos eventually becomes positive again, which I guess will be somewhere down the line. It doesn't really matter to me, though, so I didn't bother to work it out. But anyway, you could also call it, I guess, minus pi over 4, I guess would work, which means it's 2 pi minus whatever that is. I can't be bothered to do that in my head. So okay, we have this set up, and now I think we're good to go, because we're doing a surface area integral here. So we look at the formula book, it's in polar form, so we're going to use this. And I think I'm just going to integrate between 0 and pi over 4. So those will be my two limits for this integral here. And yeah, I've got some work to do. I've got to work out r squared, which I actually have, that's good. I need to work out dr by d theta, so I'll do that. I actually did some implicit differentiation here, 2r times dr by d theta. And then I just sort of rearranged a little bit, and then I squared it, and I put that in there. And now here, this is probably not the correct way of doing it, but what I decided to do was factorize out a 1 over r squared from this. And now I can root this 1 over r squared to make a 1 over r, which will cancel with that r, which I thought was really good because I couldn't be bothered to actually find out what r was, and I didn't want to deal with any square roots. Now this actually works out really well, because r to the 4, if you square that to get r to the 4, you make this, which you can then put in there. And now you can obviously factorize out a 625, root 625 is 25, I believe, but also that leaves behind a cos squared plus sine squared, which is just 1. So this works out really, really beautifully well, and you just end up with this. The sine theta just comes from there, because this just becomes 1, and then root of that is 25. You can bring the 25 out, you can integrate sine theta for minus cos theta, and then you can put the limits in, and you'll end up with exactly what they wanted after you factorize out 2, I guess, or a half, and you get this eventually. So k is 25 will be the correct thing to do here. Okay, according to the model, show the length c to d is this. Now, the important point is d here. Now, this is CP Corpore 2 stuff, where we want to find a line that, or a tangent, sorry, to the polar curve that's tangent to, that's parallel to the initial line. So here's a line tangent to the curve that's parallel to the initial line, which remember is going downwards. So therefore we're looking for dy by d theta is 0. That's from the Corpore 2 book, if you need a refresher on that. Now of course y is just r sine theta. So let's differentiate that according to theta. In fact, then, sorry, no, that's not, because of course that would mess up r. So let's square it out to get this, and then replace that r squared with more thetas. And now we can differentiate to find dy by d theta. Again, some more implicit differentiation can get done there. And then you can do some product rule here. You can verify that I've got that right, maybe. And then, of course, we can rearrange and we'll get this. What happened to the y again? Y is r sine theta. So the sine thetas, you just divide by sine theta, I guess. Is that what I've done? That must be what I've done. Where did the r go? That's interesting. Am I just being an idiot? Where did the r go? What happened here? Dr. Oh, maybe it didn't go anywhere, but it's still sort of here. But I want dy by d theta to be 0 anyway. So that. No, what on earth happened here? Why am I just missing an r? I'm just an idiot, right? It's r sine theta. This should all be divided by r. Oh, of course, but if you just divide all this by r, it doesn't matter, because you're going to set it to be 0 anyway, and then you times both sides by r, and you just get 0 equals this. Okay, cool. So I ignored writing an r here, because I knew it wouldn't matter. You just times through, and it just goes away anyway. So you end up with this. Now, I rearranged that to be this, divided by 25. There's probably better ways of doing this from here than what I did. But what I did was I said, this is 2 sine cos, just based on the thing, which means I could cancel out some more causes. Theta isn't going to be 0, because I can see that theta isn't 0. So I think I'm okay to cancel out some causes here. Cos 2 theta is cos squared minus sine squared, and then you can add sine squared to both sides, divide by 3, divide by cos squared, and you get this, which you can square root, and then you maybe know from GCSE exact values that this happens when you're at pi over 6. So I think this here happens when theta is pi over 6, and this here happens when theta is minus pi over 6. So this line here is the line theta equals pi over 6, and that intersects there. And then minus pi over 6 is this side. Now the reason that's helpful is because I can work out my r then. If I know theta is pi over 6, just shove that into there to work out your corresponding r value. So I did that, and I got r is this, which I can rationalize, I guess, for that. And now I have that length there, then 5 root 2 over 2. And I also have this length here, just by symmetry, is also 5 root 2 over 2. But this angle here is pi over 6, which means this angle here is pi over 3, otherwise known as 60 degrees. So this triangle is isosceles, because these two are the same, but it also has 60 degrees here, which means it's equilateral, which means this is also 5 root 2 over 2. And we'll have our entire question done, as show that it's 5 root 2 over 2. Good, that's the whole paper. Apologies for some slip-ups there and some mistakes, but I think we carried it through, and I think it was fairly clear as to what we're doing. So thank you for watching, and I'll see you next time.